Hello, and thank you for being here for following this session about open sourcing the IoT. During this session, we will see how it's possible to use an open source platform based on a messages as a service platform in order to build IoT solution. I am Paolo Patierno. I am a senior software engineer in Red Hat on the messaging and the IoT team. I'm lead and committer for different Eclipse Foundation projects, like for example Hono. We will speak about Hono in a few during this session. Even on PAHO, which provides some different implementation in different languages for the MQTT protocol. And then I am maintainer for different Vertex components strictly related to the IoT world. I am also Microsoft MVP on Azure and IoT. I like to blog, to speak, even on messaging, IoT, and on embedded devices. What's the agenda for this session? First of all, I will have a brief introduction on messaging, how the messaging world is strictly related to the IoT. So how IoT is just a specific use case of messaging. Then we will move speaking about EnMasse, an open source messaging as a service platform. We will see what are the main features that this platform provides, what is the architecture of this platform. And then we will move to Eclipse Hono, one of the Eclipse Foundation projects that can use EnMasse as the underlying messaging infrastructure. Then how an IoT solution can be deployed if we build such solution on the previous component, like for example on Masse and Eclipse Hono. And we will have time for a demo showing how these platforms work. So let's start with a brief introduction about messaging. What is messaging? Messaging, it's clear, is about exchanging messages. They can be exchanged internally in distributed systems or externally between different systems. All the communication happens at the application level, and typically all the messages go from a sender and a receiver that can be named as a producer, consumer, publisher, and subscriber. It sometimes depends on the protocol that we are using for exchanging messages. The messages can be exchanged in different ways, like for example in an asynchronous way, where the sender and the receiver don't need to be online at the same time. So it provides even time decoupling between sender and receiver. Or the messages can be exchanged in a direct way, so in a synchronous way. In that case, sender and receiver must be online at the same time in order for the receiver to get the messages from the sender. In the messaging world, there are different patterns that are used for exchanging messages. The most common patterns, well known even for all the people who know the HTTP protocol, for example, is the request response or request reply pattern, where a client sends a message to a server and the server replies to the client with the response for that message. Then there is the publish subscribe pattern. In this case, the producer or the publisher sends the same message, in this case the X message, to more subscribers. So we have more destinations for the messages that the publisher is publishing on some address. In the last case, the competing consumers. In this case, we have a producer, one or more consumer, but it's different from the publish subscribe use case. In this case, in the competing consumer case, each consumer will get just one of the messages that are published by the producer. So the message X to the first consumer, the message Y to the second consumer, the message Z to the last consumer, and so on. It's different from the publish subscribe use case where the same message is published to all the subscribers. Then another important concept in the messaging world is the quality of service. There is a different quality of service which specify how and when the messages are received by the consumer on the consumer side. So for example, we have the simpler, which is the at most once, even known as the fire and forget. In this case, the producer sends the message, the first message, which will reach the consumer. In the second case, the message Y, for example, will not reach the consumer, but the producer will continue to send the next message, so the message Z. In this case, it means that the producer isn't interested in to know if the message reaches the consumer. Then moving to the at least once, it means that the message will be received by the consumer at least one time. So the message X will reach the message the consumer. In the second case, the producer sends the message, but the acknowledge from the consumer is lost on the network during the communication. In this case, the producer will send the message one more time. It means that the message Y reached the consumer two times in this case. This is the reason why the quality of service is named at least once. The last use case is related to the exactly once quality of service, where there is a more complex acknowledgement between producer and consumer, and when every single message is received by the consumer just one time. Now, why I have introduced the messaging word before speaking about IoT? I can say that maybe in the past messages and messaging was not so cool for developers, but today we have IoT. IoT is considered just a specific use case of applying messaging. So we can say that the IoT is all about messaging, as we will see during this session. So we can say that using a scalable messaging platform, we can just move the Internet of Things world. If we think about the millions of devices that can be connected to an IoT platform, in that case we need a messaging infrastructure, because all the devices will send and receive messages to and from the cloud services that are in charge to handle and to manage all these devices, all these connected devices. So when we speak about IoT, we are just speaking about a specific use case of messaging, of using a scalable, in this case, messaging platform. So in this case, what an IoT platform is and what makes an IoT platform, what are the main components that we can see in a less or even more complex IoT platform. First of all, we can see in this picture that at the bottom we have a messaging infrastructure, because as I said, IoT is about messaging, because we have to exchange messages between all the connected devices and cloud services that are in charge to get all the data from the devices when we speak about telemetry, as we will see in a few minutes, or for example for control these devices, so for sending commands in order to execute some operation on the devices and in their environment, and getting the reply of such executions. So it's all about messaging, and we need, as the first layer of an IoT platform, a messaging infrastructure, an infrastructure able to exchange messages in a scalable way and reliable way. On top of the messaging infrastructure, we have some different services that we can name them as IoT core services, because we have, for example, the authentication and authorization component, because we need that the device are authenticated and authorized to execute some operation in the IoT platform. So for example, sending data on just receiving command and executing some operations. Then we need a device registration component, for example, because the IoT platform needs to be aware of the device that can connect to the platform itself. So a device needs to be registered before we can get data from these devices, or we can control such devices. And for example, another component related to the device provisioning, so handling the provisioning of these devices on the field, even updating the firmware or something like that. So we can see that the main components of an IoT platform are the messaging infrastructure at the bottom and some different IoT core services which are around this messaging infrastructure, which add some value to the messaging infrastructure in the specific IoT use case. Then on the other side, we have some business services, because when we get all the data, all the telemetry information from these devices, for example, we can execute some action on that data, or execute some command and having control on these devices. So for example, there are different components that are in charge for monitoring the devices, or for executing real-time analytics on this data, or even, for example, some machine learning algorithm for getting some future evolution of the data based on the current data that we are getting from the devices now. And we can extend all the other components that we have in a business service on the business service side. So these are all the components that we can imagine that can make an IoT platform. Even speaking about IoT, as we already spoke about messaging, even in the IoT space, we have different communication patterns. In this case, between devices and the cloud, and all the services in the cloud. First of all, we have telemetry. Telemetry is just a one-way communication from the device to the cloud. In this case, the device sends some data, telemetry information, to the cloud, to the service in the cloud, without expecting any replies from the cloud. The second one is the inquiries. In this case, the device asks for some information to the cloud service and then wait for such information from the cloud. So this is a two-way communication from the device to the cloud and then back from the cloud to the device. Then command, even known as command and control pattern, where in this case, as the opposite of the inquiry, the cloud sends a message to the device, which means asking to the device to execute some operation in the environment where the device is living in that moment. And then the cloud service waits for a reply from the device, if the command was executed or there were some problems, and so on. The last one is notifications. This is quite the opposite of the telemetry pattern, but in this case the communication goes from the cloud to the device, and the cloud is sending, the cloud services send some information to the devices without expecting any replies from them. Now, when I told that there is a relationship between messaging and IoT, and even that IoT is a specific use case of messaging, it's even true speaking about communication patterns. Because, for example, the messaging patterns can be mapped to the IoT communication patterns. So, for example, the telemetry and notification are just something like publish, subscribe in the messaging world. And command and inquiry are something like request and response, request and reply in the messaging world. In the IoT and even in the messaging as well, we have different protocols, like for example the MQP, MQTT and the HTTP, which implement all these different patterns in different ways. Some of these protocols implement just one of these patterns. So, for example, the MQTT is strictly related to publish subscribe, HTTP is strictly related to request response. And for having, for example, the other pattern, so having, for example, request response with MQTT or publish subscribe with HTTP, we need just to add some layer, some more application layer on top of the application logic on top of the protocol itself. There is, for example, instead the AMQP protocol, which provides all these different patterns. So with the AMQP we have even the publish subscribe pattern and the request response pattern. They are just provided out of the box at the protocol level, so we don't need to add some application logic, some business logic at application level for having such patterns when we use just the AMQP protocol. You can find more information about these differences in the following articles I wrote for the D-Zone website. Now, about IoT protocol, another important aspect to consider is the interoperability. In the IoT space we have a lot of different protocols, and that's true even in the messaging space. So speaking strictly about IoT, we have, for example, MQTT, COAP, MQP1, HTTP and so on. And it's not important to have one protocol which is able to be used instead of all the other protocols that we have today. The important thing is that the IoT platform that we are using is able to support different protocols, not just one, in order to have different devices able to connect to such platform. So the important thing from an IoT platform perspective is to support different protocols and not just one, or not having just one that rule them all, for example. What are the offers that we have today, speaking about messaging and IoT in the cloud, for example? We have different offers from different big companies. So, for example, from Microsoft, the Azure offer with the Service Bus and Event Hub and the IoT Hub, and then the offers from Amazon, from Google, from IBM. What are the problems that we can have with such different offers from these different big companies? The first big problem that we have is that they are not open source, and in general there is an advantage having a solution being open source. Just for IBM, for example, the Message Hub is based on one open source platform, which is Kafka, but it's not true for all the other offers. The other problem is that we can't install this solution on-premise, for example. They are available only in the cloud, so from Microsoft Azure, from Google, from IBM, and from AWS, from Amazon. It means that we have to start using this solution just in the cloud, even if we don't need the same scalability that we have with the cloud, because we are going to develop a simple IoT solution for starting with just 10 devices, for example, or something like that, and maybe scaling in the future to 100 or 1000 and so on. But in this case, we have to start to work in the cloud, and we can't install this solution on premise. And it's not so simple. Another problem, it's not so simple to swap from one cloud solution to another, because, for example, if I start today a solution based on IoT Hub, then, for example, Microsoft will increase the price for this service, and I can afford this kind of prices. Then in this case I should move to a different cloud provider, for example Amazon. But it's not so simple to move from a cloud-based IoT solution to another, just considering all change that I have to apply on the device side. So on the firmware, for example, having these devices connecting to a different cloud IoT platform, or even on the application side, so speaking about all the services, all the business applications that are in the back end and which are in charge for getting information or handling all the devices data. So migrating from one solution to another is not so simple. It can be complex. So this is the vision for this new platform, this new project, which is EnMasse. EnMasse is a platform which have as main goals to provide a scalable messaging as a service platform. It's completely open source. It can run as different containers, because it's provided by different containers running on OpenShift or on Kubernetes, for example. Here there are all the information related to this project, so the official website, the GitHub repo, and even the Twitter account. What are the main features that EnMasse has today? First of all, EnMasse as a messaging platform, as a messaging infrastructure, provide multiple communication patterns. So all the communication patterns that we saw in the previous slides. So request response, publish subscribe, and competing consumer, even known as just point-to-point. Then it supports two different messaging mechanisms, which are store and forward and direct messaging. We will see the difference between store and forward and direct messaging in a little bit. It's of course a scalable and elastic messaging infrastructure, because we want to use EnMasse for connecting 1,000 and so on number of devices in the IoT space. Today it has supports for MQP1 protocol, which is the main protocol used by EnMasse even for internal communication between all the different components, and we have an MQTT protocol support using an MQTT gateway, as we will see in a bit. In the future there will be an HTTP support for sure, for example. EnMasse is focused to be simple to set up, for management and for monitoring, and even for multi-tenancy. So having different instances of the messaging infrastructure for different tenants, in order to have one tenant not able to see the messages which are flown through the other tenant instance, for example. And one of the main aspects is that EnMasse is deployable on-premise or in the cloud. So this is a big difference with all the other offers that we saw before in the previous slide, where we need to start and stick to be in the cloud, not having the solution deployable on premise, so in our farm, for example. What's the basic idea of EnMasse? We have here a router network. The router is a project coming from the Apache Foundation, Apache QP Dispatch Router, which is a component which acts as a MQP1 router, so provide a feature to send messages between, in this case, a producer and a consumer, providing direct messaging, as we will see in a bit. At the same time, in EnMasse, we are providing even brokers. The brokers are ActiveMQ Artemis brokers, which are hidden by the routers to the producer and the consumer. So from outside, for example, when a producer connects to EnMasse and the consumer connect to EnMasse, they just connect to this router network that can be just made of one router or can be scaled to more routers. And then if we need to store messages, we can deploy even broker inside EnMasse and so on. When we start to create new addresses that can be queue topics in the broker's word, or for example just anycast or multicast addresses for connecting in a direct way producer and consumer, EnMasse just deploy by itself all the needed components which are hidden from the users, from a user's point of view. This is the main idea that we have behind EnMasse. So what's the difference of having routing and brokering in this case? So having a routers network and even brokers behind these routers if they are needed for our use cases. When we have a broker in the middle, in a messaging infrastructure, when the producer sends a message, the message reaches the broker. The broker accepts this message. So the producer has no information that the message reaches the consumer, because the consumer could be offline in that case, so time decoupling in this case, and a fully asynchronous communication between producer and consumer. When the consumer will come back online, it will get message from the broker and will accept that message to the broker. So it means that we have two different contracts, one between producer and broker and one between broker and consumer. There is not an end-to-end contract between producer and consumer. This is provided by EnMasse when from the EnMasse console, as we will see during the demo, you can create an address that is the abstraction of something like a queue or a topic. So the broker provides us a store and forward mechanism. So it can get the message, store the message, and then the message is sent to the consumer later, for example, if the consumer is offline in that moment. It's completely different of the router and how the router works. In this case, there is an end-to-end, only one contract between the producer and the consumer. So the producer sends a message to the router just forward the message to the consumer, and the consumer will accept that message, and acknowledge will forward by the router to the producer. So in this case, when the producer receives the acknowledge, it knows that the message reached the consumer. It means that the router implements something like a direct messaging between producer and consumer. The router doesn't take ownership of the messages, like the broker, for example. It doesn't store messages. There are no backing storage for storing messages in this case. We can have with EnMasse different kind of direct messaging. We can have anycast, where one producer can send messages to different consumers, but just one of them will receive that message. So something like a sort of competing consumer, a point-to-point communication. And then we have a multicast address. available in EnMasse that we can create in EnMasse, where when a producer sends a message, this message will be received by all the consumer, so in a broadcasted way, that are listening on such address. So this is the big difference between using a router and using a broker, and this is something that is hidden by EnMasse from a user point of view. The user can just asking to have this kind of behavior, so having a store and form mechanism or having a direct messaging mechanism, and then the EnMasse will deploy the needed components for having such behavior. So digging into it, what are the main components which make the EnMasse platform? Here we have the router network, which is based on the QP dispatch router from the Apache Foundation. Here we have one or more brokers. It depends if we deploy some addresses where we need store and forward mechanism. So for example in queue and topics, it means that we could not have brokers at all in our solution if we can just rely on direct messaging through the router, for example. All the communication between these components are encrypted, are TLS based, and they are based on AMQP1. Then we have an administration console used for creating addresses, for monitoring addresses, and so on. We have an identity management system based on Keycloak, because all the clients which connect to such platform need to be authenticated and authorized for sending messages, for getting messages, and so on. Here we have an MQTT gateway, because as I said, all this platform is based on MQP1, but we want to have devices, MQTT based devices able to speak within EnMasse. So on this side we have MQTT clients connect through the MQTT gateway through EnMasse to EnMasse using this MQTT gateway. But at the same time we have different AMQP based client, for example even JMS clients connecting directly to EnMasse. All this platform is running or can be deployed on Kubernetes or even on OpenShift provided by Red Hat as an enterprise version of Kubernetes with more features. Regarding the MQTT support, I like to say that it's not just having a protocol translation. So we don't have just an MQTT gateway which handles, of course, all the communication between EnMasse and the MQTT clients that we have outside. It's not just bridging or translating MQTT to MQP protocol, but the MQTT support that we have in EnMasse, it is about having MQTT over MQP. I mean having MQTT features over the MQP protocol. The main example is, for example, the MQTT last will and testament LWT feature that we have only in the MQTT protocol. This feature is about having a MQTT client sending a will message to the MQTT broker when it connects. What's the purpose of this message? The client says, when I will die, because I don't send a disconnect packet at MQTT lever, or just because the TCP connection goes down, for example, just sends this message for me on this topic. It means that if we have some other different clients subscribed to this topic, they will receive the notification that the first client is died, without sending a clean disconnect message to the MQTT based platform. So the name's last will testament feature. Now, using the MQTT LWT component that we have in EnMasse, this feature is available on top of MQP. It means that not only an MQTT client, but even an MQP client can connect to EnMasse, providing this will message information to the platform, and then when the TCP connection, for example, will go down for any reason without detaching the MQP link in a clean way, this message will be sent to all the connected clients which are listening on such address, so to MQP or even to MQTT clients. So this is the reason why I like to say that we have MQTT features over MQP. So it's not just a kind of translation from MQTT to MQP protocol. So these are the main features that we have in EnMasse as a scalable messaging platform. What's the relation with EnMasse and the IoT? As I already said, IoT is strictly related to messaging. IoT is just a specific use case of messaging stuff. And EnMasse itself can be used as an IoT platform. There is another project from the Eclipse Foundation, which is Eclipse Hono. Eclipse Hono is a platform which provides connectivity for devices. The first goal that we have with Eclipse Hono is providing device connectivity. The second one is providing even a uniform API for interacting with all the device, regardless of the protocol that we are using for that. So, for example, this platform, as we will see in a moment, provides out-of-the-box connectivity for devices connecting using MQTT or HTTP. But the user can just implement its own protocol adapters, because this support for MQTT and HTTP is provided in terms of a protocol adapter, because as we will see in a moment, even the Eclipse Hono platform is based internally on the MQP1 protocol. So we need some translation from MQTT and HTTP to MQP, something like the EnMasse platform, for example. Hono provides device-level authentication. It provides multi-tenancy, and the underlying messaging infrastructure is not something strictly related to Hono, but can be changed. The main the limit that we have is that this platform needs to be MQP1 compliant, so we need to have a messaging infrastructure able to speak MQP1. Of course, Eclipse Hono provides horizontal scalability and an end-to-end flow control between devices and the backend services that we have in the cloud. So, what are the main blocks which make the Eclipse Hono platform? On the left side, we have just the devices. Here we have some protocol adapters. As I said, Hono today provides two different out-of-box protocol adapters from HTTP and MQTT. These protocol adapters translate HTTP or MQTT in the MQP1 protocol in order to connect to the main components inside Eclipse Hono. We have the API endpoints, because as we will see in a moment, Eclipse Hono provides different API for telemetry, for command and control, and so on. There is an authentication service for authenticating this component inside the Eclipse Hono, but there is another component which exposes the credentials API for authenticating devices, for example. Then a device registry, which in the Eclipse Hono project is just an example of implementing a device registry. There is a device registration API exposed by Hono, and the customer which want to use Eclipse Hono for device connectivity can just implement its own device registry, just exposing the API that Hono needs for being aware of the device that can connect to the platform, for example. Then here we have the messaging infrastructure. The messaging infrastructure in this case is, for example, EnMasse, but could be something different. For example, out of the box, Eclipse Hono provide a messaging infrastructure just made by one router and one ActiveMQ Artemis broker, not a scalable messaging infrastructure like could be EnMasse. But it can be changed in something like RabbitMQ and so on. On the other side, we have business applications that connect directly to the messaging infrastructure for getting the telemetry data, for example, from the devices, or for controlling the devices, sending them commands. As I said before, there is an end-to-end flow control between devices and the business applications on the other side. So, taking a look to the Eclipse Hono, what are the API which this project exposes outside? First of all, the telemetry API. Every API defines what is the address where the messages need to be sent by the devices, or what is the address format where the device, for example, will receive some messages from the business services, speaking about command and control, for example. What is the format of the messages in terms of headers, of the body, and so on. The telemetry API is about sending data from devices to the cloud, so it's used by device to send data downstream to the messaging infrastructure, and it uses, for example, direct messaging. So in the messaging infrastructure, using, for example, EnMasse, with the telemetry API, we just use direct messaging between the device and the business application on the other side that needs to be online for getting this data. Then we have the device registration API, because Hono needs to be aware of the device that can connect to the service. So we have this API in order to register, deregister, get information about the devices. If a device isn't registered to Hono, it can connect to Hono for sending telemetry data, for example. Then we have the event API. It's similar to the telemetry API, so this one-direction communication, one-way communication from device to the backend to the business services. But in this case, it's used for sending event and not just telemetry data, where events can be, for example, alarms. And it's not using direct messaging, but it's using store and forward mechanism. So in this case, a broker is used in order to save these events, these alarms from devices, because we want to store, we want to save these alarms, for example, if the business application is not online in that moment, but it will get these alarms later when it will come back online, for example. An important thing that is supported by a store and forward mechanism in a broker is the TTL, the time to leave, because we want, for example, that even an event or an alarm is stored by a broker. We don't want that this event we will process later, for example, after 1 hour or 2 hours. We need, for example, that the event needs to be processed after at maximum 1 minute, but not after 1 hour or 2 hours, because it can't make sense, and it depends on our use cases, of course. So for this reason, using a store and forward mechanism with a broker, we still have the TTL feature for the messages in that case. Then we have the command and control API, for example, which is today is in draft. Is still in draft, so it's not implemented or completely available in Eclipse Hono. It's about sending commands from the business application to devices, of course. The command execution on the devices side can be just in time or deferred. Just in time means that the device just execute this command and then reply to the business service with the result of this command. Or maybe it can be deferred. It means that the device get this command, then replies to the business service just saying that it gets the command, but the command isn't executed yet because it's a long run command, for example. Later, the device will send the result to the business service in this case. There are other API strictly related to credentials and authentication, for example. The credentials API are used by the protocol adapters because they are needed for getting and retrieving credentials used by device which authenticate and connect to the protocol adapters. Using different protocol like MQTT and HTTP. Different types of credentials can be supported in this case, so pre-shared key, hashed password, public key, like certificates, and so on. On the other side, there is even an authentication API, which is used for authenticating the internal components between different components that we have in Hono. For example, protocol adapters, the Hono messaging layer, which is in charge to handle the connections with the device through the protocol adapters, and so on. So all the components, as for example it happens in EnMasse, where all the internal components have an authenticated connection using TLS, that's quite the same in Hono, for example. Now, we saw these projects. So EnMasse has a messaging as a service platform, and Eclipse Hono that can leverage on EnMasse as a messaging infrastructure for providing devices connectivity. But how can we deploy such solutions? Speaking about just EnMasse, speaking about Hono with EnMasse, and so on. We can just start on-premise, for example, maybe because our IoT solution is not so big at the starting point, so we have just few devices connecting to our servers. Then we can move to the cloud, when we'll see that our solution is becoming bigger and bigger, because from 10 devices we are moving to 100 devices, 1,000 devices, 10,000 devices, and so on, million of devices. Sorry. We can move from on-premise to the cloud. We don't need to change anything from a device point of view or from a business application point of view. We can just deploy EnMasse or Hono in the cloud, so in different platforms, as we will see in just a moment. Maybe we should change some connection string for having the device connecting to a different server from the previous one, for example. But we can just move our solution as it is today from on-premise to the cloud. Or for example, having a hybrid solution, so having some components running on-premise, some other components running in the cloud. It's strictly related on something we call today edge computing, for example. As we said, we can deploy on-premise, in the cloud, on hybrid solution, because these platforms works using orchestrator like Kubernetes or OpenShift that we can just use on Amazon, on Azure, on the Google Cloud Platform, for example, or using from Azure, for example, an Azure Container Services which provides a Kubernetes cluster. So in this case, we don't need to build our Kubernetes cluster by ourselves, something that we need on AWS, for example, using virtual machines on EC2 and so on. So we can run our platform moving from a cloud provider to another without changing anything from an application point of view, just deploying the messaging and the IoT platform on different cloud providers. It's just simple. Now, as demo, I will show in a bit this kind of solution. We have EnMasse deployed on the OpenShift, running in this case on my laptop, for example, but it could be running on a cloud provider, on Azure, on Amazon, and so on. So we have on the left side some devices, different devices that could be MQP or MQTT based, sending temperature values on an address that we defined as /temperature address. These messages are forwarded by the dispatch router network to a Spark streaming application. Spark is a project for handling real-time data stream, and for processing this data in real time in order to get some value from that. In this case, for example, we have a simple Spark driver which handles these temperature values from different devices and just process the max temperature value every 5 seconds. Then this max value is sent on a different address, which is a /max address, and it's routed to, and these messages are got by another application running on OpenShift, which is something like a thermostat application, which has some rules. So even if this max value is outside of some range, so it's lower or higher than some minimum or maximum value, the thermostat application just send a command to one or more devices in order to open or close a valve. In this case, just an example. So we have address like /control/device X, for example, and we have the devices getting messages from these addresses in order to get commands from the platform. All these messages are backed by an Artemis broker. So we have a temperature topic and different control topic in order to store these messages. So we will see in a bit how practically this solution works. So this is the OpenShift console where I have already deployed EnMasse and all the other components needed for this demo. Regarding EnMasse, we can see, for example, the address controller, which is in charge for creating an address space and handling the creation of all the addresses inside that address space. Then the administration component, for example, that exposes a console, so a web UI for handling such address spaces and the related addresses, as we can see in a few minutes. Then we have the key cloak component for authentication, so for creating new user in order to access to EnMasse, to handle all the addresses, for enabling, for example, in this demo, the devices to send the data to the platform and so on. Then the components related to the MQTT protocol, so the MQTT gateway in charge for translating from MQTT to MQP, and then the MQTT last will and testament component for handling such feature. And then, for example, the router component, that in this case is just one, so the simple deployment provides only just one instance of the router. Then using the console that is here, for example, I have created the three addresses that I need for this demo. So I have a temperature address, which is a topic, a max address, which is a Anycast address, so it will use just the router as a direct messaging address, and then the control address, which is a topic, and we will use the using a hierarchy for sending commands to devices. So for example, we will have address like control/device1 or control/device2 in order to send commands to different devices during this demo. This console provides you more other information. So for each address there are the number of messages come in and come out, how many senders and receivers we have, and so on. And there is also the dashboard which provides an overview about all the exchanging messages on all the available addresses, and here the senders and the receivers as well. Other than that, the key cloak component provide its web UI in order to handle the authentication stuff, where I have already created some users for accessing the console and for enabling devices to send data to the platform. As you can see, for example, there are two other components, which are the control pod and the temperature pod, which are related to the temperature and control topics that we have created using the console. These are topics, so they need a broker for storage the messages that are sent by devices. This is the reason why we have such components here. Other than EnMasse, here we have the thermostat application, which will be in charge to get the max value processed by the Spark driver application, as I explained before, and then sending command to each device. And here we have a really simple Spark cluster made by just one master node and one slave node, and a Spark driver pod, which will be the application, the temperature analyzer application, which will be in charge to get the temperature values from the devices, processing the max value in the last 5 seconds, and then sending an alarm on the max address, where the thermostat is listening in order to send then specific commands to the devices. So first of all, let's start, for example, the Spark driver. So as you can see now, we have just 0 pod, so no application running. Then we can scale up in order to have one instance of this application running, and at the same time we can start, for example, the thermostat application as well, so scaling up from 0 to 1. We should see that now we have sender and receiver on the temperature topic, and one receiver on max address, which is the thermostat application. Now we can just switch to the console in order to start two different kinds of devices, an MQP device and an MQTT device. I am using the Maven Java plugin in order to execute this heating device application. For example, starting the AMQP application, we will see that in a few moments the application connects to the service, just start to send temperature value, and then for example here a message is received because the settings for the current demo are related to have a temperature outside the range between 15 and 25 Celsius. In this case, in the last 5 seconds, because the device sends the data every second, we have this value outside of the range. So this is the reason why the thermostat application got the max value from the Spark driver application, then send this command to close the valve, in this case to the control/device2 address, because this is the device 2. The application is running and the same thing is happening. As we can see, at the same time we can start a device based on the MQTT protocol, so it will connect to the MQTT gateway, subscribe to the address for receiving commands here, and then we should see a command here. We are received when the temperature here, for example, is outside of the range because it's 29 degrees. So as you can see, we have two different kinds of devices based on AMQP connecting to EnMasse, and MQTT so connecting to the MQTT gateway, sending these values. The values are processed by this Spark application in order to get the max value in the last 5 seconds, and then the thermostat application is in charge to send related commands to device. So it's just a complete end-to-end solution from device to the backend, processing some data and then sending command to the device. we can just take a look, for example, at the configuration for this device, which is quite simple. We have, for example, for the MQP based device, the host name. So this is the messaging service exposed by EnMasse, which is based on MQP. This is the port, because the connection is encrypted. So this client are using a server certificate. Then we have some other settings, like the address for sending temperature, the address for receiving commands, the username and password for authentication to the EnMasse platform, and so on. And the same thing from the MQTT, for the MQTT device, where here we have a different OpenShift service, which is not the messaging service exposed by EnMasse for MQP based communication, but the MQTT service for exposing the MQTT gateway. All the other stuff is quite similar. So even in this case, the communication is encrypted on TLS, and there is the authentication with these credentials. So this is the overview of the demo that show this kind of complete IoT end-to-end solution from device to the backend and business applications.